Okay, this is our final lesson on the topic of nucleophilic substitution reactions, in which case we consider mesylates and tosylates as good leaving groups. So what motivates our foray into this area is the question, are there any good leaving groups other than halogens that are easily accessible from alcohols? So if we look back at the lesson on leaving groups, remember I had a table showing some leaving groups and showing its conjugate acid and the pKa of the conjugate acid. The following two entries were on the table. So of these two entries, the top one, so both of them are good leaving groups. They have conjugate acid pKa's of -6.5. And the top one is a mesylate or methane sulfonate. And the bottom one is a paratoluene sulfonate or tosylate. So both of these leaving groups or molecules that contain such a leaving group are what are called sulfonate esters. They are derivatives of alkyl sulfonic acids, which are similar to sulfuric acid, but not quite as strong an acid. Because sulfuric acid, with 4 oxygens bound to the sulfur, there are the inductive effects stabilizing a minus charge on one of those oxygens, thus enhancing the acidity of sulfuric acid and giving it a pKa of -9. In the case of the alkyl sulfonic acid, you still have, when you remove the hydrogen, a highly resonance stabilized anion, but you don't have the inductive effects on top of the resonance effects. Okay, so just bringing us back to something we talked about in a previous lesson. So mesylates and tosylates are prepared by reacting alcohols with either methane sulfonyl chloride or paratoluene sulfonyl chloride in the presence of a base. Okay, so let's look at one of these reactions. Again, we'll use ethanol, which is my favorite alcohol to use in these problems. And methane sulfonyl chloride is CH3S double bond O double bond OCl. So these two reagents will react together to form ethyl mesylate. And the base that is used, a good base to be used in this reaction, is triethylamine. So first of all, it's not aqueous, so water as a nucleophile would react with methane sulfonyl chloride and destroy it. So you need a base that's soluble in organic solvents, and furthermore, it's not going to be a competing nucleophile to react with the mesyl chloride because it does not have a proton to lose. It is a tertiary amine, so therefore it cannot make a neutral product if it should happen to react with mesyl chloride. So I have drawn here the full structure of ethyl mesylate, but we frequently use a shorthand where mesylate is indicated OMS and tosylate is indicated as OTS. All right, let's look at the detailed mechanism of mesylate formation. So this is going to look very similar to the mechanism that we saw for the reaction of alcohols with thionyl chloride, but there are two differences. One difference is not that important. The sulfur in this case has 2 double bonds instead of 1, so we have to carry an extra SO double bond through the entire process. Okay, so step 1 is going to be attack of the alcohol and the sulfur, and at the same time breaking one of the SO pi bonds, just as we saw in the case of the SOCl2 reaction. And then again, just as in the case of the SO2Cl2 reaction, we reform the SO pi bond and kick out the chloride as the leaving group. So we've now come to a molecule in which you have the oxygen still having its hydrogen on it, but it's been activated. Now comes the important difference between mesylate formation and the SOCl2 reaction. And that is because we have a base present, the next step is deprotonation of the acidic hydrogen to make a neutral compound. With SOCl2, the strongest base we had present was Cl-. That's just not actually the alcohol itself is a stronger base even than Cl-. But they are not strong enough bases to achieve this deprotonation. Triethylamine is a strong enough base, and one of the themes that's going to come up again and again in this course is that favorable Bronsted acid-base reactions are faster than any other class of organic reactions. Okay, so this is going to be a favorable Bronsted acid-base reaction. You take the proton and pick it up with the electrons from the triethylamine, break the OH bond, and now you make the neutral sulfonate ester product. And the byproduct is triethyl ammonium chloride. Okay, so now once we have the mesylate or the tosylate, what do these reagents do? Well, they now serve as electrophiles in SN2 reactions. Okay, so an example using a tosylate this time around and using the OTS abbreviation that I clued you into on the previous slide, we have Cn- as a nucleophile coming in. This is a secondary alkyl halide, but it's still a small secondary. So it comes in from the back side. The OTS is kicked out, and the Cn- takes its place with dashes instead of a wedge because we had inversion of stereochemistry. Okay, so the use of mesylates and tosylates then is to start to allow us to put together two reactions. So a mesylate is a stable compound. It's something you can put in a bottle and you can store it till next week if you need to. As opposed to an intermediate which reacts rapidly in the course of the reaction mechanism to get to a stable product. So if we want to use a mesylate, that is forcing us to do two different chemical reactions in two different flasks, possibly on two different days. And the way I indicate that in problems is having a two-reaction sequence, where the problem we would have to solve is to fill in these boxes in the two-reaction sequence. So this problem tells you to start with butanol and react it with mesyl chloride, and the product of this reaction then is going to be the mesylate. If I were giving this to you on an exam or on a homework problem, I would have to include a base also, but I'm just kind of giving you the outline of this on this slide. So that in the first box goes the mesylate, and then over the second arrow is a nucleophile. This is an enolate ion, remember those? They're good nucleophiles for forming carbon-carbon bonds. And then the final product has to have a new bond formed between the nucleophilic atom of the nucleophile and the electrophilic atom of the mesylate, which is the carbon that is bound to the oxygen. Okay, and the way this is going to look as the final product is we simply add a butyl group to the carbon that previously had a negative charge in the enolate. Okay, so that's how you would handle one of these problems in which you have to fill in the two boxes in a two-reaction sequence. So as I said at the top of this lesson, this is the end of our series of lessons on nucleophilic substitution reactions. What we will start to consider next is a related class of reactions called elimination reactions. And when we get there, we will see that under the set of conditions where so far we've only been considering nucleophilic substitution, in many cases something else can happen. And that's going to increase the complexity of all of these reactions and force us to analyze in much more depth what can happen under a certain set of reaction conditions.